and welcome to the Geomistic channel. Today we're going to tackle the dreaded word problem in the context of right triangle trigonometry. We'll define a few keywords and give you some tips to make sure you're drawing accurate representations of your problems, and at the end we will walk through some common examples from start to finish. Go down to the description and click on the link to access a guided notes worksheet if you'd like to take notes as you follow along. Now, some of the trickiest aspects of word problems is trying to get an accurate picture drawn and to determine what values go where in your picture. Problem is, all it takes is one misplaced value and you are totally sunk on the whole problem. So let's talk about a few keywords that will help with the placement of your values. So the first keywords we're going to talk about are angles of elevation. Spell right, and angles of depression. Okay, angles of elevation and depression. You're going to see these terms quite a bit in these types of problems, and they're best defined with the help of a little diagram. So what I'm going to do is I'm going to draw a little picture starting with the ground and a person on the ground looking up at a bird in the sky. Okay, so the line of sight from the person to the bird looks something like this. Okay, so we've got a line of sight from the person to the bird. If the person were to be looking straight ahead, you would have this line right here, so that's parallel to the ground, and say the bird was flying straight ahead as well, which would give you that line, also parallel to the ground. Okay, so what I've created here are two angles, and one of which would be considered an angle of elevation, the other of which would be considered an angle of depression. Question is, which one is which? You might think elevate, which means up or rising, and depress or down. You might think the bird is up in the air, so that's an elevation, and the person's on the ground, so that's depression. It's not quite right. The definition of an angle of elevation would be an angle formed by a horizontal line and then a line of sight to an object above. Okay, so if I'm thinking about an angle of elevation, I have to have a horizontal line, and from that horizontal line I have to be looking up. So we're talking about right here. So the horizontal line of the person looking straight ahead and then looking up toward the bird, that angle rises, it elevates. So this right here is your angle of elevation. Okay, and in contrast, the angle from the bird, again looking straight ahead, so the horizontal line. Okay, an angle of depression is an angle formed by a horizontal line and the line of sight to an object below, which would be this right here. So this is your angle of depression. Now the key word here really is the horizontal line. Okay, so these angles of elevation and depression always must start with the horizontal line and look either up or down depending on if it's elevation or depression. Now not always are these specific words elevation and depression used, but any iteration of looking up or looking down at a certain angle, it's always going to start with that horizontal line. We're going to talk about a common mistake with that here in just a second. So one of the biggest errors, or at least most common errors that I would see, is if, for example, maybe somebody was in the top of a building looking down at something on the ground. So say somebody's up here looking down at an object on the ground, and the problem says that the person at the top of the building is looking down at an angle of depression, let's just say of 20 degrees. So what happens is you draw a line from the person up in the building to the object on the ground, and because it says the person's looking down at a 20-degree angle, you think, well, I got this triangle here. If they're looking down at a 20-degree angle, that's got to be here, right? Again, that key word in an angle of depression is the angle has to be formed by a horizontal line. So it's really not this one at all. So my 20-degree angle, if the person is looking down, I have to start with if the person were looking straight ahead, parallel to the ground. So the angle of depression has to start at the horizontal and it has to travel downward. Okay, so the 20-degree angle is really up here. Now you might think, well, that's not part of my triangle that I've drawn. Not always is it going to be. The good news is, since that line of the person looking forward and the ground, since those are parallel to each other, I can utilize that these two angles are alternate interior. And if the lines are parallel, alternate interior angles are always congruent. So that person looking down at the 20-degree angle of depression, I can kind of translate that down into this angle of the triangle. And now I've got one of my values in the triangle, right angle here. Okay, so it's an easy mistake to make. Just remember the horizontal line is kind of that starting point. Okay, so to help you visualize how to create a picture, a couple of other words to kind of look out for. Anytime they talk about a vertical line or an altitude or a height, we always know that those values are going to be going straight up and down. If it says the distance from one value to another is a certain value, I always just want to draw a straight line from that, from those two points of interest. So the distance from again, a person at the top of a building to a point on the ground, I'm looking for that oblique line, or that hypotenuse usually is what that is. Now, if a problem says that a device is used to measure an angle, and the device has a certain height, we can't forget to add that into our problem. So we have to take that into account. So maybe it says a person on the ground is measuring the height of an object with a transit or a theodolite or some kind of measuring tool, and they tell you that the person is a certain height, that does it does play a part in the problem. So let's go ahead and do an example with a problem like that. Okay, so we'll start with the word problem itself. We'll start by reading it, looking at the values, and then we'll draw our picture and then solve. Okay, so here's the first one. While standing 40 feet from the base of a flagpole, 6-foot-tall John measures the angle of elevation to the top of the flagpole using a clinometer, finding it to be a 24-degree angle. How tall is the pole? Okay, so if we look at the values that we have, we can see that the person measuring the angle is 6 feet tall, so we know that's going to play a part. The person is standing 40 feet away from the base of the flagpole, and we've got a 24-degree angle of elevation. So those are the values that we have to use to figure out how tall the flagpole is. Now, this particular word problem, it's not too difficult to kind of visualize what's going on here. If I'm going to be drawing a picture, I know that I have a flagpole and a person, so just draw the ground right here. We've got the person, we've got the flagpole. Okay, so two objects. We know the height of the person, we don't know the height of the flagpole. So if I kind of start building my picture, the person is 6 feet tall, the flagpole is unknown, that's what we're trying to find, so we can put an X right there. The other values that it gives us are the distance away from the person to the base of the flagpole. So notice it says the base of the flagpole, which is right there. So if the distance from the person to the base of the flagpole is given, that's going to be right here on the ground. So that says it's 40 feet. Okay, the last value it gives us is the angle of elevation from the person to the top of the flagpole. Now, if the person is measuring the angle, usually that's going to be with their eye. If they're using a clinometer, it's just a little tool that you can look into. It'll tell you what the angle is the person's looking up at. So the person's eye to the top of the flagpole will be that value, that distance right there. And again, it's always good to get the horizontal line of sight so we know where our angle of elevation is going to be. Okay, so anytime it says, again, angle of elevation, I'm going to have a horizontal line. So if the person's measuring the angle from their eye, straight across would be here, looking up to the top of the flagpole, my angle of elevation is going to be right there. And it says we have a 24-degree angle of elevation. All right, so here's our picture. Don't forget this is right triangle. So I've got right angles here. This dotted line is parallel to the ground. Okay, so once we have our picture set up, we kind of have to decide where we're going to start. We've got our right triangle right here. I can move my 40 feet up to this distance there, since I know it's 40 feet away from the base of the flagpole. I can just translate that up to get it as a value in my right triangle. Okay, so the height of the flagpole is what we're missing. We've got our triangle here. Last thing I want to do is I'm going to translate the height of the person over here. Okay, and the reason I'm going to do that is because when I solve for the missing side that I'm looking for in this triangle, I'm really only going to get this distance. Okay, this is the distance that I'm going to find in the triangle, and then what I can do at the end is I can add in that extra 6 feet to get all the way to the ground, so I know the whole height of the flagpole. Okay, so I'm going to call this distance right here, I'm going to call that y. Okay, so x is the entire flagpole, y is going to be this portion. I'm going to add 6 at the end to get the entire length of the flagpole. Okay, so our picture's good. I'm going to utilize sine, cosine, tangent. I'm going to write SOHCAHTOA right over here. Left-handed problems. SOHCAHTOA right there. In my triangle, my angle is 24 degrees. That's right here. I've got, where's my pen? I've got this side over here, which is my opposite leg. I've got this side right here, which is my adjacent leg. My hypotenuse here is kind of unnecessary. I don't have it, nor do I need it. So opposite leg is missing, adjacent leg is known. Opposite over adjacent, this is going to be a tangent problem. So to set this up, I'm going to write the tangent of my angle 24 degrees equals, tangent is opposite over adjacent, so that's y over 40. And I put this over 1 to create my proportion. Okay, at this point, I'm going to go to my calculator, put it right up here. Go to my calculator. Once I cross multiply this, I'm going to have y times 1, which is y. 40 times tan 24 is what I'm going to type into the calculator. So I've got 40 times tangent 24. And what do we get here? Looks like it's about 17.8. Okay, so I got y equals 17.8. Now, is that the height of the whole flagpole? No, that is not. That is just this distance right here. Okay, to get the entire height of the flagpole, what do I have to remember? Height of the person measuring the angle, which is this distance. So if I add 6, okay, add 6 feet to that, and I'm going to get my final answer, which is going to be 23.8 feet. Okay, 23.8 feet for the entire height of the flagpole. Always double check your labels. Make sure you look at what your problem is asking you to round to. This one I didn't tell you. I went ahead and rounded to the nearest tenth. All right, let's look at another. Okay, next word problem. Mary looks out from the top of a 150-foot lighthouse to a boat coming into the harbor at a 32-degree angle of depression. How far is Mary from the boat? Okay, so again, an accurate picture is really the most important part before we start solving anything. We have to make sure everything is in the right place. So really two things that are going on here. We've got a lighthouse and we've got a boat coming into a harbor. So start with kind of a ground level. I have a lighthouse. We've got Mary at the top of the lighthouse. There she is on the roof looking down at a boat in the harbor. So we got a boat. Okay, the values that we are given, only two this time. It says the lighthouse is 150 feet and Mary is at the top. And it says she's looking down into the harbor at the boat at a 32-degree angle of depression. So just two values. Now, the question is asking how far is Mary from the boat? Okay, so if we're looking for the distance from Mary to the boat, how far is Mary from the boat? I'm just going to draw a straight line from Mary to the boat. Okay, so this is what we're trying to find. That's the distance. It tells me the height of the lighthouse, which is 150 feet. So if I drop a line straight down from Mary at the top, down to the ground, again at a right angle, we've got 150 feet. So our triangle is coming together nicely here. Last thing we're given is the angle of depression from Mary to the boat. Okay, so again, this is where you have to be a little bit careful. The angle of depression is not going to be inside of that triangle because this angle here is not formed with a horizontal line, so I have to get that first. So Mary looking straight out from the top of the lighthouse would be this line of sight parallel to the ground. Looking down at the boat, this is my angle of depression, which it says is 32 degrees. Okay, so this angle not being inside of my triangle is no problem. Because these lines here are parallel, I know that this 32 degree angle and this angle down here, these are alternate interior, which are always equal when the lines are parallel. So I can translate that down to the bottom. Okay, so I've got my right triangle, I've got an angle, I've got a side, I'm missing a side. That is all I need to be able to figure out that distance. Okay, so let's do it. So we've got, we'll just write it right here. After you do problems like this enough, you can kind of phase out your mnemonic SOHCAHTOA. I'm just going to write it just as habit. Okay, so let's decide, is this going to be a sine, cosine, or tangent problem? To decide, I'm going to label my sides. Here's my angle. Opposite of my angle is here. The leg adjacent to my angle is here. Notice there's nothing there. My hypotenuse, what I'm missing, is right there. So I know hypotenuse is important, that's what I'm trying to find. The opposite leg is known, so I'm using the opposite leg in relation to the hypotenuse. O and H, opposite and hypotenuse, that's right there. So this is going to be a sine problem. So to set it up, we're going to write sine of 32 degrees. Sine is opposite over hypotenuse, that's 150 over hypotenuse is x. Complete by proportion, and I'm left with this. So let's go ahead and cross multiply. 150 times 1 is 150, which is equal to x times sine 32. And then last step to solve for x, to get x by itself, I'm multiplying by sine 32. So to get rid of that, I'm going to divide both sides by sine 32. Sine 32 over sine 32 is 1, so I've got x equals 150 over 150 divided by sine 32. So I'll go to my calculator. 150 divided by sine 32. And 150 divided by sine 32, it looks like it's about 283.1. So again, rounding to the 10th. And we are in feet once again. So the distance from Mary at the top of the lighthouse to the boat in the harbor, 283.1 feet. Okay, doing great. Let's do one more. Okay, last one. Brothers Bill and Ted leave their home and race to a 600-foot tall building down the street. The faster brother, Ted, begins to pull away, and at one point they both look up to the top of the building, Ted looking up at a 41-degree angle of elevation and Bill at a 35-degree angle of elevation. How far apart are they at that point? Okay, so this one can be a little tricky just because we've got really three things going on here. We've got a building and we've got two brothers racing toward this building. So in this particular problem, there's really kind of two problems that we have to solve to be able to get to our final answer. Now Now, a couple things to make note of. First of all, that Bill and Ted are both leaving their house. They're leaving the same house, meaning they're going to be both on the same side of this building that is down the street. So if you think they're running in a straight line toward the building down the street, they're both going to be on the same side of that building. So if we think ground level, we got a building. We've got Bill and Ted both running toward this building from their house. Ted pulls away, so they're going to be at different distances away. So we got two guys. Notice it doesn't give the height of each brother, so we can assume that the height of each one is negligible. They're going to measure the angle of elevation to the top of that building. We'll just assume from the ground. Okay, so here they are. Each one looks to the top of the building. Like so. And we know the height of the building is 600 feet. So I'm going to go ahead and drop this line down. 600 feet. Okay, so we kind of have two triangles going on here. We have a smaller triangle from Ted, who is the faster brother, so he's going to make it to the building first. And we got Bill a little bit further out. Okay, so it says that Ted is looking up to the top of the building at a 41-degree angle of elevation. And then Bill is at a 35-degree angle of elevation. Now these two angles, because we've got this horizontal line, the ground, each one is looking up, assuming from the ground, since we don't have the height of each brother. I don't really have a triangle, but I'm going to assume I should have made it from the bottom instead of from their eye, but let's just go ahead and say that this is a triangle. Ted looking up at a 41-degree angle, and Bill at a 35. Okay, so the question says, what is the distance between the two brothers? So this is really what I'm after. Now this little piece right here isn't a side of a right triangle that I have in my picture. But if I kind of think through what I've got, if I can figure out in this triangle, if I can figure out the distance from the building to Ted, then I can do the same thing in the bigger triangle, the distance from the building to Bill. The difference in their distances away from the building will be the distance that they are apart from each other. Okay, so again, I can think of it as, if I can find this distance here, which I'm going to call that distance A, and I can find this distance here, which I'm going to call B. I'm totally off my page here. Okay, this distance here, which I'm going to call B. Okay, the difference between those two, so the green line's B, distance, or the difference between those two values is going to be the distance those two brothers are apart. Okay, so I've got two problems to solve. No problem. So let's start with the smaller triangle right here. Here's my angle. Opposite of my angle is the 600 feet. Adjacent to my angle is what I'm looking for. Shouldn't have used A for adjacent, but it's okay. So adjacent and opposite are the two sides that I want. That hypotenuse is really unnecessary. Opposite over adjacent, this is going to be a tangent problem. So let's set it up. Tangent 41 is equal to opposite, 600 feet, over adjacent, which is unknown. Cross multiply of 600 equals A times tangent 41. And to solve for A, divide by tan 41 on both sides. Tangent 41 over tangent 41 is 1. I'll have A equals 600 divided by tangent 41. That's what I need to type in. So we've got 600 divided by tangent 41. Looks like we got 690.2. 690.2. Okay, so this distance right here is 690.2 feet. Okay, now I'm going to work this same problem, but instead of using Ted is my point of reference. I'm going to use Bill. So his 35-degree angle, looking at this triangle, I'm going to find this entire distance from the base of the triangle to Bill. Okay, once I get that, I can take that value and subtract the 690.2. That'll tell you my distance between the two guys. Okay, so let's go over here. So again, really it's the same setup because my angle being here, opposite is still 600 feet. Adjacent is going to be this length B. So it's really the same thing, just instead of 41, I'm going to use 35. So I've got tangent of 35 degrees equals 600 over B, whole distance down here, that's the adjacent leg. Cross product once again, I've got 600 times 1, B times tangent 35, and divide both sides by tangent 35. Which gives me B equals 600 divided by tangent 35. And we've got 856.9. Okay, 856.9 feet. Alright, so my two values, distance away from the building to Ted, 690.2, distance away from the building to Bill, 856.9. If I subtract those two values from one another, that's going to give me the distance between the two. So we'll go 856.9 minus 690.2. And we got 166.7. So I've got x equals 166.7 feet. Will be the distance between Bill and Ted. Okay, so as you can see, some of these can take a little bit of time, a little bit of work to set up and to solve. But as long as you have your vocabulary down, you know how to put your values where they need to go using those little hints that we've talked about today. You can solve these no problem. So that'll do it for today's lesson on right triangle trigonometry word problems. Thumbs up if it was helpful, and subscribe to the channel if you would like to see more lessons like this. Thanks for watching, and we'll see you next time.